the binding energy curve in a more detailed way. So here we go. Look at this color. There. So we have the binding energy curve. Generally, as you know, is given by the binding energy per nucleon, A, and then suddenly we have a sudden increase, as we know, it's kind of goes smoothly down. What is bothering me here? Cell phone. Prof. Moyes wants to call me, but he will have to wait. Let's close all this WhatsApp nonsense. All right. So this was the case, and we approximated for the where is my cursor now? Here we go. We approximated for the helium 4, the range of the nuclear force. As you remember, the delta X was approximated to be the range of the nuclear force. I mean, the radius of the alpha particle, where the alpha particle was given by 1.2 a to the 1/3 Fermi. But we could have also approximated close by maybe to carbon 12, and the radius of carbon 12 would have been more like the radius of carbon 12. Some books they also approximate to carbon 12, so as the step rise, sudden increase up to carbon 12. So in this case, we will have a little bit more, like 2-4 Fermi or something, no? So 1.2 times 12 to the 1/3. That gives us like 2.75 Fermi. So this could have been also another option. Probably is closer to nature. But anyway, the purpose of today is to try to understand the physics behind the I found this the semi-empirical mass formula, how we can approximate something which is microscopic. As you know, the binding energy is always given by the mass of the constituents, the mass of the proton times the number of protons plus the mass of the neutron times the number of neutrons minus the mass of the nucleus itself, which we call it XA. Let's give that outside here, right? And obviously, all this is multiplied by C squared, as you know, and then multiplied by 931.494 MeV per C squared. We have an atomic, or call it atomic mass unit, but it's just call it a U. So then, how we interpret that our range of the nuclear force was the helium-4, and this sudden increase in the nuclear force, we see that there's a huge difference between the nuclear force and other forces like the gravitational force, right? So in the gravitational force, if you have many 1 kilo or 2 kilos, right, and you have here, let's look at this fellow who is holding all this weight for us. Okay, so if you add all these kilos, right, the more kilos you add, the stronger is the gravitational force, right? And doesn't matter, you can add a whale on top, and it will add to the weight in a way that poor Albert Einstein here, he will feel shaky at the beginning, and finally he will be overwhelmed by the weight on top. All right, so now The same thing happens with charges, right? The more positive charges, obviously, the larger will be the Coulomb force, right? But what happens if you add proton and neutrons together? The situation doesn't seem to be such. And what will be that curve? You know, how the Coulomb force, the gravitational force will increase as you add all particles together. Let's say, let's change here the color, or let's make maybe 4 particles. Let's see that they're interacting 4 particles like we have for the helium, right? Helium-4. But let's say they are charges or masses, so 4 kilos. So these guys will interact with each other. They will have this interaction. This guy will interact with this fellow, with this fellow, with this fellow, this guy with this fellow, and this guy with this fellow. So you add the interaction between all these 2 guys, between each of the 2 guys composing these 4 bodies. So you will have that this will increase as n plus 1 divided by 2. So there are 1, 2, 3, 4, 5, 6. So 6 interactions in which you have 4 plus 1 particles 5. Let me see. 1, 2, 4. Yeah. 4 and minus 1 here. You know, you don't remember. So that will be 4 minus 1, 3. 3 times 4, that will be 12 divided by 2, 6. So in the binding energy curve, if we have all these interactions, obviously the more particles, the more interactions you will have. And eventually you will have that the binding energy curve will be expected to change as a minus 1 over 2, depending on how many particles you add to the nucleus, right? So how this will be look in our binding energy curve, how this will look like in our binding energy curve per mass. Basically, we will have a shooting all the way up as it will happen for the masses, right? The masses, the gravitational force will also increase according to the interaction between these 2 bodies, and the Coulomb force the same. So this will give us the number of interactions that we have, and we will expect this roughly the binding energy per nucleon to be proportional maybe just to A, right? Basically, a straight line going up there. But what we see is that you have a sudden increase, and then suddenly you have what we call a saturation of the nuclear force, as you know. So in principle, the binding energy, this is telling us that there will be a constant here, and it basically will be proportional to the mass number, but not to the A plus 1 that we were referring right now, right? So basically, when you do the binding energy over A, this will be equal to a constant, right? Which we call the volume constant. So there's a volume term in the Bethe-Weizsäcker formula, which is given right here. This is the volume term. This EB is the binding energy, so which is proportional to A, and then these factors subtract to the binding energy that we have. So for instance, this term here, the A to the 2 over 3 is the surface term, and considers that they will be in a nucleus. Obviously, the guys on the surface, they won't have any neighbor here to interact with, and they will be less bound than the guys inside the nucleus, right? Which will interact with each other. So this is the surface term. So then we have the two terms, which are the binding energy. Let's call it binding energy is equal to AVA minus A surface A to the 2/3, right? To the 2/3. So now we have this formula, and we are going to keep exploring what other phenomena we can add to the binding energy curve, so we eventually can reproduce this curve that we are so familiar with, right? So obviously the nucleus also have protons, and the protons are positively charged, right? So there will be a repulsion from all these protons inside the nucleus, and there should be another Coulomb term, right? So that Coulomb term can easily be deduced from electrostatic. Basically, you can use the divergence of E. This is actually Maxwell equation, E naught. You can use Gauss and have this in a volume. So basically, you have a volume here, and you have different charges, and the divergence of the electric field will be equal to the integration of rho dV over E naught, where this is basically the charge inside the Gaussian sphere, this symmetrically uniformly charged distribution for our nucleus. And then we have that Maxwell equation give us this, but then Gauss theorem tell us that V delta E, divergence of E dV is equal to the closed loop of this ds, where ds is now the surface, is the flux of the electric field going through that surface that we have defined. So basically, from here, from Maxwell equation, the first Maxwell equation, where it tells us that the electric field is created by this source, in particular, source of charges, right? Like in our case, we remember we have the divergence of B is equal to 0. So that's why the other day we said that there's no magnetic monopoles, because no one has found them, although many people are looking for them. And but according to Maxwell equations, there's no source of the magnetic field given by a kind of magnetic charge, right? So basically, we can deduce this formula. We can use this formula equal to the charge divided by E epsilon naught, and we can have that E 4 pi r squared, and that's the radius, right, is equal to Q epsilon naught. So basically E is equal to Q 4 pi epsilon naught r squared. And similarly, for the potential, we have that is the charge 4 pi epsilon naught r. So we can deduce what is the work needed to bring a charge from infinity to the point where we want to measure the electric field. That is called the work done, which is the difference in the potential. And we basically can deduce the equation which provides a solution to this problem. So that would be, let me just quickly open a new one. Yeah. So So that will be the work done. I want you to get this. Actually, I'm going to give you the solution, which is 3/5 of 1/4 pi epsilon naught q square divided by the radius of the nucleus. Okay. This q square obviously is equal to 3/5/1/4 pi epsilon naught not a square z square. Okay. So we can actually determine what is the this is actually equal to the difference in the potential. We can determine what is the potential energy in a nucleus according to a charge distribution with charge Q or Z, E is Z. And we can apply this for any nucleus. So the potential energy of whatever nucleus you want to put here, say 40 calcium. Or, you know, you can make your own little Excel file and say, okay, calcium 40 is going to be equal to, we use the Gauss system. So this is 1.44 MeV Fermi. Basically, the whole calculation is very simple. It's 3/5 of 1.44 divided by the radius here. Z square, whatever is the Z, calcium 40 is 20, and divided by 1.2 times 40 to the 1/3, right? So we have the Fermi. This one is MeV Fermi. The Fermis will cancel each other, and we have everything in MeV, which will give us something like 1.44 times 3 divided by 5 times 20 square divided by 1.2 and divided by 40 to the 1/3. That will give us a value of about 84 MeV. Obviously, you do the same thing for 235 uranium. So then you will have 235 here, and whatever is the charge of uranium, obviously you will have a much bigger number. I will give you an estimation of the repulsion of uranium 235 and how much. That's why you need a little bit of ping neutron to hit the uranium 235 and split it into two, as we saw it. So basically, we have another term here in the binding energy, which will be AVA minus AS A to the 2/3. And then again, now we have minus, and we can put all these things into a constant, which we're going to call AC. And then we're going to have Z square over A to the 1/3. So this will be the repulsion of the nucleus according to the proton number and the mass number, right? So obviously, for Z equal to 1, there's no repulsion, but still, this is adding to the binding energy, which doesn't make sense. So what we're going to do is to change that. We're going to have AVA minus AS A to the 2/3 minus AC Z minus 1 over A 1/3. And you can see now that for Z equal to 1, this is equal to 0, right? Okay. So far, so good. You know, we have, but let's see actually. Let's see actually what we want to achieve now. Now we are setting up an equation which we want to compare with data, right? So with data, we have our mass evaluation, which you have in your lecture notes in the lessons. Chapter 1, nuclear properties. You have the mass evaluation for 2020. You have the charts of the chart of nuclides, and you have this Python script which I just added to the chapter 1. And I would suggest that you download this right now from the Canva, because we're going to start working on that. And also, you need to download these guys. Put this the mass 2020, the text file, and the Python energy, put in the same directory. And we're going to do some calculations and explain a little bit more on the Bethe-Weizsäcker or the semi-empirical mass formula. Okay, I give you a couple of minutes to download those files. So go ahead. And I'm going to keep sharing the screen. I hope by now you have picked up the Python code, and you have, because we're going to run it now. So let's see what happened. Yeah, tell me.
Where were we supposed to download the code? Because I went on your Canva and I can't see anything.
Okay. So on Canva is under lessons. We go down to nuclear properties. And here you have the binding energy Python script.
Okay, thank you, sir.
All right, so give you a couple of minutes. So also you have to download this one, right? The latest mass evaluation from 2020.
Jimmy, Prof, how do you download them? Because I opened them, but I don't see the download.
Save link, and don't put it wherever you want. Right click, okay. Save link. Okay.
Okay.
The same thing with everything. Right link, and right click, save link as. All right. So this is how I actually got this one here. These are all the atomic mass numbers, and you can Control S. I open with Emacs. You can do Control S, and you see here this I search, and say we want to know 40 calcium. So I type 40 space calcium, and here we go. I get the mass excess for calcium 40, which then I can then convert to atomic mass units or whatever. Okay. As you know, the binding energy is basically applying Einstein's formula of, in this case, delta M C squared, right? So now we go up here. I have opened the code right there. And you know, this has been many years of people have been working and getting the latest coefficients from the Bethe-Weizsäcker, which is our semi-empirical mass formula. They obtained these ones from the mass evaluation 2016. You know, we could do the same thing with the mass evaluation 2020 and get a publication. That would take us not too long to do that. But, you know, these are the coefficients here that they are claiming: the volume coefficient, the surface coefficient, the Coulomb coefficients. These are the asymmetry or the symmetry coefficient, and this is the pairing coefficient, which we are going to deal with in a little bit. But so far, I want you guys to appreciate these are the coefficients that I have been using. You know, 15.75 is probably not very far away from the value that these guys are claiming. You know, 14.6. The surface is 14.07. I have here 17.8. That changed a little bit, but basically 0.711. We can also go to the Wikipedia, and you will have different sets of parameters there. Let me see, where are they? Probably there's a little table here at the back, the bottom. Here we go. See, they're different depending on the book. Iceberg and Resnick is a beautiful book for quantum mechanics, and you have different coefficients there. You can see, here we go. 15.76 sounds quite familiar. 50.75, you know, 17.8 compared to 17.81. So this one is quite similar to the one I have, 23.7. 23.7 actually is probably the same. So this one comes from this reference, which was Alonso Marcelo Finn. Oh, actually, I love this book also. Fundamental University Physics, Volume 3. So as you can see, but there's a bunch of different options. They are close by, and these are fits to all the masses, right? What we do here, and actually this paper is it shows it nicely. We get all the masses for independently of, we put all the masses for any A together, and then whatever A is, you get the same mass number, you average and get your typical data point here, right? In an empirical mass formula, you are comparing with each value has an A. However, this data point is the average of several nuclei with the same A, right? Or you just average all of them and get this data point. So this is how it is done. And you have this bunch of nuclei. As you can see, not every nucleus has the same binding energy, the same mass number. It differs quite dramatically depending on where you are in the nuclear chart. So obviously, these fellows here, they're going to be more unstable. They're going to be less bound than the ones close to the line of stability. because as we say this morning, there is a large energy gap here, and they are more difficult to be excited. So these nuclei, they are more stable, right? So everything is being connected now. And now, if we want to see what is happening, I have it here. I can look at what is producing, and these coefficients with the mass, the atomic mass evaluation for 2020, it actually reproduced quite nicely the values of interest. We can always go here and get a better indication. Again, I show how to, I'm going to move this up. I show how I just running it, Python 3, and then the name of the Python. So I don't know how you did this in your Windows 10, Nikita. Can they do this anyway?
They can install Python on Ubuntu, but I also showed them how to use Spider on Windows.
Right. So anyway, they want to.
Yeah, and the mini school as well. Last month they were using another way. Yes.
The Jupyter, whatever, right?
Yes.
So there are many ways. There are many ways for you. I myself, I'm old-fashioned. I open the terminal, but there are many notebooks. You know, Spider, Jupyter, which will help you to visualize things in a way. I prefer just to look at the code, see what the code is doing. Here is the energy. As you can see, what the code is doing is just this energy actually is the binding energy per A, per mass number. This A basically is binding energy per A, because as you can see, the AV parameter doesn't have any A here. The A here to the -1/3 should be A to the -2/3. So basically, all this term here is being divided by A in a way that we already get the binding energy per A, right? So in such a way, this is quite nicely reproduced, but you know, there's no perfect solution, and this is an effect of the shell model. See, what we see here, when we see this the difference between the atomic mass evaluation, right, and the semi-empirical mass formula, atomic mass evaluation, this bump here corresponds to a magic nucleus, and you can actually see it better here in this PDF, this lecture note, which I found very interesting at the end. Right. So at the end, you have the semi-empirical mass formula. It was an old plot. Maybe now we're getting better, but you can see these data points which deviate from the semi-empirical mass formula for the simple reason that here we have more stability, because here we have a shell structure, those magic numbers that we have discussed in this week, and these magic numbers, they add more stability to the nucleus, which is not considered in this simple semi-empirical formula. All these things, all this playing with coefficients, must always be seen with how do you say, a grain of salt. You don't really trust things. Coefficients normally are a consequence of our ignorance. So the more coefficients you have, the less we know the situation. Although here in this particular case, I like it because we are interpreting each term in a way which kind of makes sense and maybe provides us with additional information, as we see now with the symmetry energy term, or with the, as we have seen before, with the volume term, which leads to saturation. You know, you can look at the interaction between particles and see that it doesn't follow the. But let's see what happened actually. If we multiply, we reduce all these terms. We multiply by A. That will imply that we have this adding charges together, right? As we just mentioned in this particular case, where Einstein was going to be, squeezed by all these charges, all these kilos. So now we, instead of following the pattern that we should expect something like that going up, right? If we change the binding energy term, so if we just do, let me see, if the binding energy per nucleum is equal to this constant multiplied by A. This will be like having everything as a function of A squared, right? So this is what we are doing in the Python script. And as let's multiply also with 0.5, because as we saw before, that was the number of interactions, right? So Control X, Control S, Control X, we save it and see what happened now. So we have removed the rest of the coefficients, and now we are playing to see what happened. Nothing happened. And let's also, because these coefficients are fitted to the data, and if we have removed all the rest of the coefficients, let's remove this guy. So let's make this 0.5, and let's leave this 0.5. I'll remove this 0.5 here. Control S, and then let's see what happens. Okay. Times A, and this, I want this just to be 0.5. Control S, here we go. And then here we go. As you can see now, now this is shooting. The semi-empirical mass formula has shoot all the way up, following this trend that we were predicting before, right? So actually we can change this 6 to 10 limit if we just go here, actually 6 to 10, and we can make the 2 because that's the energy of the deuteron, right? And let's make it, we can keep this as 10. Control X, S, we save and see what happened there. So as Nikita mentioned the other day, I'm always using this and, so I can see the difference between what I did before and I'm doing now, right? And you can play around with the different parameters and see basically that this is shooting all the way up. And now you go a little bit down because there are also masses which leads to this binding energy per nucleus. So again, this is a saturation property, which may change. Obviously, in this case, there's no saturation property according to the semi-empirical mass formula, which is not the reality. That's why we need to change that here. Actually, I'm going to make this a little bit bigger. Let me see. Okay. Let's see, control. No, doesn't work. The thing you can see this on the screen, right? Let me see. Oh, that's for searching. Okay, so we change this. Let's go and change it back. So to the parameters that we have here before. And now again, we have removed this A square dependence on the volume term. We're going to go back here to 2. All right. So now, let's play. Let's play and say, okay, what happens if we increase this by a factor of 25, a factor of whatever? So now remember what the other day, the question I asked you, you know, if I change the range of the nuclear force by 2 times, right? If we increase the range of the nuclear force by 2 times, now we can go here and see what will happen, right? Remember I told you before that the range of the nuclear force will be the range of the something which is double the helium-4, right, in size. That will be beryllium-8, for instance. Beryllium-8 has 4 protons and 4 neutrons. The size, the radius of beryllium-8 will be the new range of the nuclear force. Or even a little bit more, probably, because beryllium-8 is actually the range of the nuclear force around that, but something bigger, a bigger nucleus. But according to our approximation, we can approximate which was beryllium-8, the range of the nuclear force, the radius of beryllium-8, and we can start playing. What happens if we, instead of 15, we put here 16? Something small, a small change. So this is nothing here. This was the first one with the fitted parameters in the Wikipedia, in the Finn's book. So if we save it now, you see, this is what is happening. So if we increase the binding energy, this is, you need to figure out how much, for instance, the binding energy will increase, binding energy per nucleon, if you increase the range of the nuclear force. But now we have a way to see what is happening. If you increase the binding energy, you increase the range of the nuclear force, the binding energy will also increase per nucleon because you have more interactions, as we just discussed at the beginning. And the saturation point will happen at a larger mass number for a heavier nucleus. Everything will be more bound, as you can see here. Even a very heavy nuclei, the 235 uranium, is also much more bound than it was before. Although remember here, this is the average of nuclei, and we have to see what happened at 235. But let's assume that this is the point here now at 235. Somewhere here, as you can see, we have increased almost 1 MeV per nucleon. And this will have consequences, dramatic consequences, in the way we look at nuclear fission. That neutron that we are sending to the uranium-235 may not be enough to split uranium-236 in two, right? So these are the consequences that we have to investigate. Now, if we assume that the binding energy is larger because of the range of the nuclear force has increased. Well, with this Python script, you can actually play around and exactly pin down that, how it will change the situation if we increase the range of the nuclear force. But not only that, we can do lots of things. We can play with the different parameters. But I'm here very interested also in the next term, which is the symmetry energy. And this term here is given by this formula. I use this Wikipedia because sometimes, here we go. So we have a symmetry energy term, which is, let's put the equation here. Which is binding energy. Now this is going to be minus a symmetry a minus z square divided by a, right? And this is the term that we have here, which is called as the symmetry energy term. Some people call it the symmetry energy, but actually I call it a symmetry energy. And basically it tells you, that the more the difference between proton and neutrons in a nucleus, the more subtraction to the binding energy will happen, right? So let's look at the nuclear chart. This is also a very important concept. Let's look, what is the chart here? So if I will draw a line here along the line of stability. So let's draw a line for n equal to z. So this is a term that we want to investigate now. So the symmetry energy term, which is given by, let's put everything together now. So we have determined that this is a binding energy, which is normally given by the mass of the constituents minus the mass of the nucleus, can be approximated by a volume term minus a surface term, so 2/3, minus a Coulomb term, which we have set minus 1 over A, the 1/3, minus a symmetry energy term, which is equal M minus Z squared over 2. So now if we look at the N over Z in the chart of, let's say this is Z and this is M, and we draw a straight line, we see that there's a lot of elements which follow that straight line. You see all these guys here will follow a straight line. And there's a point around 20 where the straight line will keep going up, but then this thing is shifting to the right? So what I want to say is that maybe all these nuclei, all these black squares, everything is following this straight line, but at some point the line of stability turn, and we have this situation, right? So basically, this is just representing that the Coulomb force is increasing, right? And here they were very stable for N equal to Z. So basically, this is the N equal to Z line. And there's a shift towards the right. We eventually need more neutrons to add to the nucleus to keep it, to hold it together, to keep it bound, right? So this is the phenomenon that we see here, M minus Z squared. So the larger is the difference between neutrons and protons, the less bound, remember, because all these guys are subtracting, the less bound will be the nucleus. So also in the shell model, we can see that. In the shell model, we can see that what we saw today, where you have the heavier the nucleus, you have these protons here, but then you will need to have more neutrons on this side to keep balance in the situation. Obviously, there's we lose the interaction between these guys. They're not close to each other. These guys are close to each other, and they actually couple with each other, and they result in a more bound system. As you move away from the line of stability, from N equals Z line, the situation reverses and you lose binding. So now this is the phenomenon that we see here, right? As you go up, you reach a maximum where fusion energy is a release of energy, and from a certain moment, this guy comes down, and that's what we see also, although not very clear, but here depends on the scale, and you can see what is happening. So I could play with these things forever and check what is happening. But now I want you to get to this to the script, to the code, and play with different possibilities, different parameters, change the different coefficients. The last one is the delta coefficient, which also we haven't talked about pairing, but pairing is also a very important factor in nuclear physics. So basically, it tells us that whenever you have a pair of protons or a pair of neutrons or a pair of proton neutrons, they actually they get coupled with each other in a way that you also gain energy. So that's a very nice exercise, which can be, we're going to understand pairing from a practical point of view. So I want you guys, let's invent a problem. So we have, let's see, boron has 3, right? 3, no, helium boron there. So let's make this 7, right? And see, beryllium 7, 4, and 3. I'm trying to find maybe let's see, beryllium 8. That would be 4 and 4. So I want you to calculate binding energies of these guys, which will take you a couple of minutes, and to investigate the binding energy of this guy with respect to this guy and with respect to this guy. Which one has more binding energy here? What do you think? Out of these 3, which one will come with more binding energy? Actually, we can make this better. Actually, we can make it boron. Where am I here? We can make boron 3, boron 5. So I want you to investigate these 2. The binding energy of these 2 guys, and calculate it and tell me what is the difference between the binding energy in beryllium 8 and the binding energy in boron 8. Which one is more bound and which one is less bound? And I want you to interpret that for this prac. Okay. So prac, one of the first questions is to interpret these 2 guys, because this guy is going to end up adding another extra term, which we don't have time to explain because it's a kind of quite complicated, but it's a very important term. You can go and read in Crane, but basically couples. The pairing means that you pair 2, and you pair 2 protons, 2 neutrons, or even 1 proton and 1 neutron. So this coupling implies that there's a large overlap between there's a reverse time where one particle goes in this way, the other particle goes on the other way. So the trajectories, they overlap very well. So this overlapping is very important because they get closer to each other. And by getting closer, the proton and the neutron, the 2 protons with each other, the closer they are, obviously, according to our potential, there will be more binding, right? There will be additional binding because the protons and the neutrons, they are coupled with each other, so they are closer to each other. And this is a phenomenon of the short range interaction of the nuclear force, right? So this is called the pairing factor. And as you see here, is determined depending on whether you have an odd nucleus or an even nucleus. That's why I'm getting you this question, which I asked you right now. And what is the equation? Here we go. This is another factor. Delta with depends whether you have an odd nucleus or even nucleus. Even or odd. Let's see again here. Delta N0. And to explain what is the difference between even and odd, you will see that even nuclei, they are more bound than odd. And the binding, the extra binding comes with for the because of the short range and the pairing interaction. You can see that from this problem that you have right here. But now I want to explore something. Let's explore a hypothesis. And let's say, okay, all this binding energy curve, all these binding energies depends on the masses of ground states, right? This is the binding energy of the ground state. When we studied the deuteron, remember, I told you that the 2.224, the binding energy, was the binding energy of the ground state of the deuteron. Let's call it R. And there was a potential that you calculated, remember, of being about minus 35 MeV. That was V naught, the depth of the potential. And there was a level here, the only bound state in the deuteron, which was a J pi equal 1/2, which has an energy of 2.224 MeV, right? So this was actually the energy of the ground state. So whenever we are applying this formula, the binding energy of a nucleus equal to the mass of the proton times the number of protons plus the mass of the neutron times the number of neutrons minus the mass of the nucleus itself, AZ. Whenever we apply this formula, Einstein's formula, basically, EmC squared, we are always calculating the binding energy of the ground state. So this is the binding energy of the ground state. So a nucleus, as we know, it has lots of excitations up there. And this is the binding energy that we calculate is for the lowest state in the potential. So now, my question is, in stellar explosions, normally the nuclei, you have a huge explosion and things decay as we have gone through the beta decay. They don't necessarily decay to the ground state. In fact, in many occasions, you have a nucleus excited at very high excitation energy, where the binding energy, as we know, will, as this is the energy, sorry, here we go. As the energy goes up in the excitation, this will be energy of excitation in the nucleus. This is the ground state here. So as the energy goes up, the binding energy goes down. Right? So the binding energy is equal to the minus excitation energy. Right? It's basically the same thing, but actually going up or going down, right? So the excitation energy will increase, but the binding energy will be reduced. It's clear. So you have a potential, the ground state is here in the depth, in the lowest state, but then you have states up there. They're going to be less bound to the point where you reach the positive side of the potential, and then there will be a repulsion, right? And there won't be any more binding to keep the nucleus together. So then I say that here happens that in a stellar explosion, you may reach the nucleus at a different level, which doesn't correspond to the binding energy curve or to the semi-empirical mass formula. And in addition, these elements that we are creating, they have a very large n minus z square, because these are produced in this chart of nuclides here, is this terra incognita, where all the elements above iron are produced. So basically, the symmetry energy term is going to be very important. So I want you to investigate this question, this point, and see what will happen to the binding energy curve if you change the symmetry energy term. So basically, I want you to play around and tell me what will happen. Actually, I want to add a new script. Questions, guys? So for instance, I want to show you this one also. And you have here the different potential, I mean, the different parameters. This has a little bit of the two of them. Here is the parameters for the nuclear chart that we're going to write down right now. So we're going, let's see what happens if I run this code. Python 3 chart 2. So basically, this is the nuclear chart. This is the more binding energy here. And you have all these elements that you can produce, right? So basically, what I want you to do here is to play with the code that I just gave you, and come with any interpretation that you think is worthwhile, any logical interpretations. So my goal for this particular prac is interpreting. So what happens if we increase this? What happens if we increase the volume term? What happens if we increase the surface term? What happens if we increase the Coulomb term? You know, I want you to explore what happens if we increase the symmetry energy term. So as I say, most likely the other terms, they don't have to vary so much. But I will stop here because I want you to investigate. I won't tell you anymore. And you can write your own essay, you know, and deduce what is all these coefficients, how they come. Actually, that will be very nice. So you deduce all the coefficients, how they are extracted. Don't only look at the Wikipedia and do a proper job, right? Look at the coefficients, explain how the coefficients in the semi-empirical mass formula arise, how they come from, what is the logic behind, and then you play with the code, with this code that you have there, and tell me what will happen if you start changing parameters and play with them. What will happen with the binding energy curve? What will happen with the fission energy? You know, what will happen with the, you know, interpret. We have our weakness so far is interpreting, and I want you guys to explore and just play and with the code, run the code, change this, change that, until you come with, wow, what is happening here? Suddenly I get this one, and you send me. You can put a bunch of, you can make a PDF, a doc file with all this information, put a bunch of screenshots there, and explain each screenshot. Okay, I want you to do that. I want to stop here, and I want to get any feedback from you guys. Questions in what is needed? It's easy, peasy. You basically use the semi-empirical mass formula, study it, different coefficients, different parts, the volume part, the surface term, the Coulomb term, and deduce how these factors are in there, and provide any pros, any cons against this semi-empirical mass formula. What is good about it? What is bad about it? I'm telling you a little story. So one time I went to Oxford, and then I gave Mariam, who's that? So one time I was in Oxford, and there was a competition for the best young student in the country for any field. So there was a guy who was like a Steven Spielberg, all this PowerPoint presentation, you know, effects, beautiful presentation. And mine was more old-fashioned, and everyone loved it more because it has some more interaction. So I basically won the popular vote, and the winner could go to Hungary to an international conference. So I was doing the PhD in England at that time. And then I forgot my backpack inside. And someone, and they were discussing who was the winner. And they were discussing between this guy, the Steven Spielberg guy, and myself. And at the end, they were discussing, and they asked me, you know, during my talk, they asked me, is this Bethe Weizsäcker, is this empirical mass formula being used anymore? At that time, I didn't know. I said, well, I don't think so. I think it's something very old. I mean, no one is using that anymore. But I'm not sure. I was sincere. I was not sure about it. So this was used by the jury, by this committee, to put me in second place and give the award to the English fellow who will represent the UK in Hungary in this international conference, rather than Spanish guy anyway. So what I want to tell you here is I didn't explore. At that time, I didn't explore this particular case, and I want you to do this and see whether you can come with something interesting, and I'm sure that you will. So that's it. I think we have done. We have a long day. So Chad, are you okay there? Shoki?
Yes, Prof. Yeah? I'm okay. Prof, for the code, if you download the stuff for the code to work, you must just rename the mesh file to mesh2. Mesh2, because if you run it it says there's no file. Of course. Yeah.
Yeah, I see what you're saying. Yeah, that when you the code, I probably gave a different number, a different name, right? So what is the code now? RS2 pi. So the binding energy, this one, Emacs. So right. So the mass file is, what is it?
The name should be mesh20.
Let me see what is the file name. Maybe I'm going too far. Let me see. What did I here we go. Amy 2020. Okay, here we go. So you can change the this is the label. This is sorry, this is the printout. So what is the actual file? Let's see, Control S. Let me see, mass. Here we go, mass20.txt, right? So yeah, you just call it as you wish, actually. Doesn't need to, you can change the name as whatever you want, right? So the mass20.txt, but you have the document which I send you, which is called mass.mass20txt, right? So you change the name, Chad is right, you change the name to whatever you like. I call it mass20.txt, but you can call it whatever, right? So ls2.txt. So here it is. I have also the mass16.txt, but I'm using the latest one. And you just call it, you know, whatever the file it is in the Canva, you save it and call it whatever you want, and just use the name that you have called it here, right? Okay, good point. Any more questions?
So are we using Python for this practical?
Using Python for this practice, I want you to run the code. I want you just to look at the code, to change the parameters, to change the view. You know, I want basically just to play, to change the name of the file. You know, as chat just call it, is called mass. Mass 20. But you can, you know, it's up to you. Whatever you call it, whatever you save the link as, whatever, then you can change the name, right, to anything you want, and then that's the name that should be in the when you read the data, right? So basically, I want you to explore. This is quite a simple code. We are actually getting the mass numbers. So let's go a little bit through the code, actually, because I think maybe it's important that we go through the code. So here we are calling. I keep, you know, read the experimental data into our data frame, right? So we just basically, if you do the following, let's actually save you some energies. So if we go to Canva and we take this file, right? We save the link as. So let's call it, okay, as it is. And let's put it in my directory where I have the Python code, correct? I put it there. And then if I go to the Python code, I will just do ls2, actually ls minus l, ls minus l, let's see, here we go, ls minus lrt, and this is the latest file I put into this directory. So then I can copy this, I can copy or I can move this file to something, you know, I can call it atomic mass evaluation 2020. .txt, right? So then here I have to call it atomic mass evaluation 2020.txt, right? Control X, I save the file, and then I can run the Python script, Python 3, and this is the binding energy. Here we go. And I can put the and if I want to do again the same thing. And you can see how it nicely fit the data, and you can always save the spectrum, you see, as a PNG, right? That you can put into your prac. Save the spectrum as a PNG to put into the prac. Explain, for instance, these little uncertainties here. They happen because these are magic numbers, and there's a difference between the predicted semi-empirical mass formula and the actual masses, because there's more binding due to the shell gaps, right? There's more energy in the nucleus. So right, you have different possibilities for markings. What is this now? I don't know what it is for. Figure options. You can change the axis also, make it bigger. So the labeling, you know, A minus Z, you can put it where it belongs. Log, you can make it a log. That's actually very nice. You can put this on log, or you can put the Y on log. Right, and then everything. Actually, let's see how it looks like. The whole thing in log. Let me just do here. Let's see how the whole thing looks in the log scale. I change here. So I want you to explore these things. Doesn't change much. Okay. So basically here, what is happening? Oh, the average binding. This is the average binding. As I say, we're averaging over all A's. So this is what is happening here. We are getting all these A's, all these binding, all these guys are in KV, right? So for each A, which is, you know, for instance, for 11, for 12. For 12, we are adding all these 12. For 14, we are adding all these 14 and making an average. But then, because these are in KV, we are dividing by 1,000 to put them in MEV, right? Because that's our our final plot is given in MEV, but the mass success in the mass evaluation is given in KV. So that's why you make the average here and divide by 1,000, right? So you take, so you can place, actually remember I use deep sky blue, but you can change the colors to whatever you want to. You know, you change the scale 2 to 10 to whatever you write in the axis, you know, and then you learn by changing things. By changing things in this code, you really learn how to use Python in a practical way. So I want that. I want a little document where you understand every of these parameters, where they come from. It comes from a fit, but the term itself, the terms here, how are the terms being determined here, and which is in Crane, is everywhere. So I want you to read that carefully and provide your input, not copy and paste from a book, but provide your insight and extrapolate. Always interpret, right? And then just play around.